This is the work solution to question 12.4 from the FEEG1003 Thermal Fluids workbook, the 2015-16 edition. So section 12 deals with viscous flow. So we've gone through, we've done questions on conservation principles, momentum, energy, continuity, and then moved on to steady mechanical and steady flow energy equations. So steady mechanical energy is the extended Bernoulli equation, so it has a couple of balancing terms to account for the losses of mechanical energy, or the conversion of mechanical energy into other forms. Now we look at problems where we have to take viscosity into account. So question 12.4 involves pumping oil from a reservoir along a long distance of pipe. I put all of the key variables that are given in the question. I'll have to refer to some notes here because there's a lot of numbers in this question. They're all fairly standard apart from Q, which is not in standard SI units, it's in meters cubed per hour. So if we divide that number by 60 squared, 3,600 seconds, we get a value of 0.347 meters cubed per second. Now in the question you're given a table of Reynolds number against friction factor, CF. So we also need to find CF. That goes into our governing equation because it's a parameter within the expression that defines wall shear stress. So we need that for later on. In order to get the friction factor, we need the Reynolds number. And in order to get the Reynolds number, we need to find the velocity in the pipe. And then we have all the terms that we need to work this way. And remember, it will be the average velocity across the cross-section of this pipe, because as you know, there will be a velocity distribution across the circular area of that pipe. So we're working out the average velocity. Right, so U bar equals Q over A. I'm not going to write it out in full, which is 4.91 meters per second. Then we can work out Reynolds number, so that is rho U bar characteristic length, which in this case is the diameter, divided by viscosity. We've got all of those numbers. You can work out the Reynolds number. So 39,280. Now we can do interpolate in the lookup table in the question. And we get a value of CF. And again, as long as you get close enough, that's fine. That's -3. Okay, and the expression that we need, CF equals the wall shear stress divided by the kinetic term, half rho U bar squared. That will come in later on, so we'll make a substitution. Okay, now what we're going to do is we're going to draw this pipe as a control volume. So we have our pressure here, and our fluid flow is going from left to right. Here we have P minus delta P, so any change in pressure acting in that direction. We've got the wall shear stress opposing the motion of the fluid. And again, that's all acting along some length L. Okay. So the next thing we need to do is to come up with an expression to show a force balance within that control volume. So what we want to do now is go back into your notes, because this is the workbook questions are all open book. They're designed to take a little bit longer than maybe a standard exam question. So you're welcome to go back and look over the notes and find key expressions or revisit the theory. And I'd always urge you to do that, because that way you're doing the question and learning as you go. And then by hopefully employing the right equations and arranging the variables so that they're dimensionally correct, it's good practice for the final exam. Okay, so we need to write basically an energy balance in that control volume. Okay, and you can probably work out you've got some sort of pressure force in this direction, kinetic term, and then obviously opposing that you've got this shear stress term. So that's the next thing we need to do. So go back and revisit your notes. And then what we'll do is we'll do a simple force balance based on the forcing pressure and this shear stress that opposes it. Okay, so I've put our calculated parameters in red on the side of the board here, and this equation here is what we need. So this is our sort of pressure forcing term. We need to work out this delta P, that's the next step. And then it's being opposed by the wall shear stress multiplied by the internal surface area of the control volume. We can rewrite this, so we can take this value of tau W and express it in terms of CF in the kinetic term. So substitute that in, cancel some terms, so there'll be a D either side, the pi's will cancel, and then rearrange for delta P. So when we do that, so substitute and rearrange, we end up with this expression, which is delta P equals 4 times the length divided by D, and then half the rho U bar squared CF. Okay, and you can put plug all of the numbers into that, and you find delta P equals 0.35 times 10 to the 6 newtons per meter squared, so keeping it once again in standard SI units. So now we've found delta pressure term, we need to do an energy balance. So if you go back into your notes, the energy required is going to be equal to the energy to overcome this internal friction plus any kinetic energy out. And then we've got a pump efficiency here. So the pump's going to have to deliver more energy in than we get out. So you need to divide that energy in by 0.6 to give us a greater number, so a greater amount of power. So again, if you're not confident in what that expression should look like, it should be, again, in section or chapter 4, the lecture notes. There's 4 lectures there. I think it's lecture 4.2. So go back in and have a quick look at your notes, and then come back and see if you've got the correct answer. Right, so if you've gone back to your notes now, or if you didn't need to, again, energy in equals delta P times Q. So that's the energy to overcome the internal friction stresses, or friction forces, plus half, again, mass flow, bar squared. And then we need to times it by, multiply it by 1 over the efficiency. So we get a larger number. Mass flow, that's just simply rho Q. So density times volumetric flow rate. So that's that. And then you can just plug in all the numbers. I'm not going to write it out, I'm running out of board space. If you do that, you get the answer in the book. And all the numbers are on the board somewhere. So you get 208 times 10 to the 3 joules per second, or watts. So that's 208 kilowatts. Okay, I'm quickly going to rub this lot off and then we'll tackle the second part, which isn't too onerous. If you read the question, it says that now the pipe diameter has changed and we have a vertical element, so we have to take into account the mechanical energy to lift, so the potential energy to lift the oil up, so rho GH. So we have to add that in as well towards the end of that part. So I'll fade to black quickly, rub this off, and we'll do part 2. Okay, welcome back. So we've got to do the same steps as before. We need to find CF. To do that, we need to find the Reynolds number, and to find that, we need to find the velocity. So the same preliminary steps we did before. Now the diameter has changed, obviously, so everything will be slightly different. So the diameter is now 0.2 meters. So we recalculate U, which is the volumetric flow rate divided by the area, Q over A. The new U can work out to be 11.04 meters per second, which means the new Reynolds number. Again, everything else is the same density, viscosity. Is 58,880, fairly close. And then our new value of friction factor CF, again, interpolate from the table, as long as you get something reasonably close, 4.97 times 10 to the minus 3. Okay, and then we work back through again, but this time we account for the potential energy term as well, because we're raising it vertically, so adding potential energy. So here's the expression. Again, hopefully refer to your notes if you've got no idea where this comes from. Again, it's a bit of rearranging. And then plus our rho GH. So we have all the numbers now for this. So we can put it in 2 times the length. The new length of this pipe, section of pipe, is 25 meters. And this vertical pipe, diameter is 0.2. Same row. The new value of cross-sectional velocity, average cross-sectional velocity, new value of CF, and then rho GH, where rho is, again, density of oil. So it gives us a delta P of 0.317 times 10 to the 6 newtons per meter squared. And then the additional power equals delta PQ, again, over, remember to put in the pump efficiency, Volumetric flow rate's the same, delta P we've just found, N is the same. Plug those numbers in and you get 184 kilowatts. So the total new power, total equals 184 plus our 208 kilowatts. So that's the answer in the book, 392 kilowatts. Okay, so that's 12.4 done. And you've seen now the issues with viscous flow and overcoming friction. And you've done the Moody diagram in your lectures, so you've had a look at that. Obviously, when you've got very long lengths of pipe, you need a large diameter pipe. That reduces friction because for a given roughness length, it will reduce your relative roughness. So if you have a roughness height of 1 millimetre, that's far less of a problem if your pipe is 2 metres in diameter. If it's 5 millimetres in diameter and your roughness height is 1 millimetre, you're in trouble. So what this means is practically, if you have a certain length of pipe, there will be a limiting flow rate that you can have. And I did some work with on this a few years ago, little anecdote now, with some architects in London. They wanted a water feature, very, very narrow jets, firing incredibly far and to stay basically as coherent jets of water. So no sort of dispersion or anything like that. So we created a manifold and tested lots of different pipe types and nozzles, and we found exactly that. When you have a 10 or 8 mil, 10 mil jet, doesn't matter how big the pump is on the end of it, eventually this shear stress, this opposing force due to friction, dominates, and so no matter what your pressure and difference, how much energy you're putting in at the upstream end, you can't overcome this. It becomes a limiting factor, so you can only go up to that. So obviously with pipelines, when they're very long, you want them to be as low friction as possible. Otherwise, you need to have intermediate pump stations to boost the pressure so that you get some kinetic energy out of the end. So that's the way it sort of works. So that's why in water supply in most countries, we try and have the reservoirs up high, and then we just basically, the potential energy turns into kinetic, so the water flows naturally down the pipe. But ultimately, when you get to, say, the base of a tower block or a multi-storey building, you have to lift the water to the highest floor that requires water, so usually the top floor, and that water has to come out and be supplied at a certain pressure. So in the UK, that's approximately 10 metres head. So you've got a 30 metre tower block. You need to make sure that at the bottom, you're delivering water at a pressure of 40 metres. It's easy to kill off the energy. We can have certain valves that will just reduce the pressure so that you can make sure that everyone on every storey has the same pressure water. But that's what you need to do. So there'll be pump stations around cities and towns that do that, and you'll see them once you know they exist. You'll probably see them around, and you'll probably know that there's a reservoir on Glen Eyre Road. That's a big grassy bank that you've probably never really paid much attention to, but that's actually a reservoir. And again, it's fairly high up in town, but there's some big tower blocks up on the avenue in Southampton. And again, that will require, the water will not flow out of that reservoir naturally and go to the top floor of that those tower blocks. So again, there'll be a pump station somewhere to boost the pressure to get the water up to the top. So that's the practicalities of real viscous fluids in engineering. And we're constantly transporting fluids, oil, water, various other things, air, in such pipelines. It's an incredibly common piece of engineering. Okay, there's a little aside for you. Hopefully you didn't find that too taxing. Best of luck with the rest of the problems in the workbook.